This example is the analysis of the small signal hybrid pi AC analysis. So for this problem, we want to find Rn, Rout, and then the midband gain of Vout over Vsig, which is our input. So to do that, let's first look at Rn. So Rn is located at the emitter side of this transistor. So in order to find the equivalent resistance from this node to ground, I have a pathway through here and I have a pathway through this transistor. I can use the resistance reflection rule to actually get rid of this by giving the effect over to the base resistors. And in that case, it's dividing the base resistors by beta plus 1. So then I can ignore this transistor and my pathway is going to go through here to ground. So that is a summation of both of those resistors. So Rn is then going to be equal to 100 plus R pi 1 over beta plus 1. R pi 1 is given as 4,000 in this problem. So that's then 100 plus 4,000 divided by beta plus 1, which is 100, so 101. And that gives me a value of approximately 140 ohms for Rn. Rout is also located at the emitter side of this transistor. So again, we're going to do the same thing where we can remove this if we account for its effect, which will be dividing the base resistances all by beta plus 1. So I can divide everything over on this side by beta plus 1. This is also going to give you a pathway to ground over here, but recall that the equivalent resistance that we saw from the top side of the transistors made it look like an open. So the pathway from this node to ground, I have a pathway here, and I have a pathway through here. So that's going to give me the parallel form. So I'm going to have 200 in parallel with everything in this branch over here. And that pathway goes through here, and then through here, and then that's an open over there. So all of those will be a summation. So it will be R pi 2 plus 1k plus 26k all over beta plus 1. And R pi 2 can be found through GM2, and recall that GM2 and R pi 2 are related by the formula of beta divided by GM2. So in this case, that's 100 divided by 4 milli, and I get a value for R pi 2 of 25k. So plugging in the 25k for the Rn gives me this value of approximately 144 ohms. So we talk about wanting a high input resistance for Rn, where ideally this is not high. We say a high input is going to be in the hundreds of Ks, 100K range. Our out is 144 ohms, which is ideally what we want, which is low. So the ideal is a low value. And a low estimate for output resistance is lower than about 1K. The next thing we want to do is find the overall gain of the output over the input. So I'm going to erase these, and now we want to analyze the output over the input. I typically like to start with the unknown that I'm trying to solve for. In this case it will be V naught. So I want to get an equivalent, or an equation for V naught. Again, I see that there's a dependent source here and a dependent source over here. If I want to try to ignore one of them, I'm going to take this as my source, which means I need to reflect this transistor. I determine the location when I use the resistance reflection rule, and that's going to be determined by where my source is located. And in this case, this would be my source, which means I'm at the base side. So I'm going to reflect everything in the emitter side by multiplying everything in the emitter resistors by beta plus 1. So now I need to find V out, and I can do V out by finding the current through this branch and multiplying it by 200 ohms. I notice here that this is a current divider, and so I can use this as the current divider with this as one branch, and this would be my other branch. So my equation for this is going to be V out is equal to, and the current is going up due to the location or the direction of this current source. So that's going to give me a minus GM1 V pi 1, and then it will be the opposite branch in this case, which is 26K, divided by the summation of both branches, and R pi 2 again was 25K, and so I'm going to put that 25K here, which was R pi 2. And then I have the 200 times beta plus 1. And beta is 100, so I'm going to just multiply that by beta by 101. So this is the current in that branch, and then I need to multiply it by the resistance, which will be 200. From here I need to find an equation for V pi 1. And V pi 1 is located right here. And again, I see my source is located in the emitter side, so I'm going to reflect everything on the base side in order to be able to ignore this. So by using the resistance reflection rule, it accounts for the characteristics of that dependent source, and then I can ignore it. And so here I see that this is a voltage divider. So this is a plus to minus location, and this is plus to minus. So the current is actually going to flow from that source in this direction, which means that it's a plus to minus direction of the current. And so I'm going to get an opposite voltage for this one. So V pi 1 is going to be a negative V sig times R pi 1 over beta plus 1. And R pi 1 was given as 4,000. And I can get GM1 the same way I got R pi by using the relationship of beta over R pi. And so this is going to be 100 over 4K, so I can get GM1. And that gives me a value of 25 milli. And I can plug those in and get V out, and then I divide by that V sig to give me V out over V sig. And plugging in all those values, I end up with a value of 51.6 volts per volts. And that is my gain, which would be considered a good gain. Typically, a gain greater than 20 is considered high.